Hello everybody, this is Professor Yogesh and today we are going to discuss about designing a Verilog program for decimal adder in Digital Design and Computer Organization Lab. And the program for decimal adder is constructed here by making use of data flow structure. And the decimal adder is all about adding any two numbers, and if the numbers resultant exceeds beyond 9, will be making that particular number to get represented in decimal format. So we all know that after 9 in binary or hexadecimal representations, after 9 the number will be represented as A, B, C, D, E, F, and then followed by 1, 0, 1, 1, 1, 2, and it goes on like that, right? So here if our numbers are added, for example A and B, right, if they are getting added, and if the resultant exceeds beyond 9, then we need to convert that number into hexadecimal to decimal number, right? So the number representations will be by default in hexadecimal or in binary formats, so that has to be converted into a decimal representation. For example, 9 plus 5 if you are adding, so the resultant is 14, right? But in the representation we get it as D, right? So hexadecimal representation of 14 is D, so it will be represented as D. So whenever we have a representations to convert, right, a number from hexadecimal number to decimal number, so we go by uh, implementing them by making use of a decimal adder, constructions. So where if the number is exceeding beyond 9, so we try to add some number to it and convert that into a decimal number. So the logic here is uh, we are supposed to add 6 to the number, to the resultant whatever we get. The reason for adding 6 to the number, right, after 9 is from 9 to 10 again in hexadecimal representation. So there are 6 alphabets which places in between, right, between 9 and 10. That is, after 9 we have A, B, C, D, E, F. So 6 numbers which are going through in between 9 and 10. So in order to convert any number from hexadecimal to decimal representations, we try to add 6 numbers, right, if the resultant is going beyond 9. So that is the logic that we use for decimal adder, and I'll straight away go to the tool which I've used for illustrating uh, the decimal adder. So the tool is Xilinx tool, as we all know, and the module name which I've created here is BCD adder, and we have two inputs called A and B, and if I need to consider even the carry, right, the carry also be can also be considered. So I have taken three input values, A, B, and carry in. A, B are 4 bits, whereas carry in is a single bit input, and two output values are sum and carry. Again, sum and carry is again 4-bit variables. So both input and output variables are declared here, as you can see, and they are declared in the vector representation. So they are not scalar because they are 4 in number. So instead of declaring them as A0, A1, A2, A3, B0, B1, B2, B3, so we declare them in the form of vector representation so that it could be declared as 3:0. So that is about declaring the input and output variables. Now coming to uh, declare them by making use of the programming part, that is by making use of behavioral programming. So in the behavioral programming, if I need to write the structure, all the output parameters whatever we have, we are supposed to declare them in the form of registers. So I have declared the register for sum as well as for carry, right? The input parameters will be retained as it is, but the output parameters will be declared in terms of registers. And I've declared one more variable called register, the sum temp. So it is a temporary sum variable, right, that will be used between loading the data, actual data, to the actual resultant, right, from the addition process. So as soon as the addition is done as I've already said, we are supposed to check whether the number is greater than 9 or not. If the number is greater than 9, we are supposed to add. So if we add, the data will be lost. So what do we do is we copy that data to a temporary variable, and then from there we do the checking of whether the number is greater than 9 or not. So for that we require one additional variable called sometime. Then in order to write the programming in behavioral structure, so we go by declaring always at statement. Now we are taking only the input parameters here for always at statement. So begin, and we add all the 3 bits. The 3 bits are A, B and carry in. The carry in could be either 0 or 1. So if you are giving a carry value, then this value will be 1 bit 1. Otherwise it will be 0. Then you are supposed to check if the sum, right? After adding, the data will be loaded in sometime. So you are checking the value in sometime, whether it is greater than 9 or not. If it is greater than 9, as I already said, you are supposed to add 6. So you can see here sometime is equal to sometime plus 6. So this will add 6 to the resultant. And if there is any bit which is exceeding the 4th bit, that is 0, 1, 2, 3, right? If it is exceeding the 4th bit from LSB, that will be considered as carry. Right? And the data whatever we have in temporary variable, that has to be copied to some variable. Suppose if the resultant is less than 9, so we don't need to add 6 to it. So we can directly take the data which is there in the temporary variable to some variable, and carry will also be declared as 0 in this case. Right? So this is the program that we have written. Now we'll see how this will generate the value. So I'll execute this. I'll check for the compilation, error, if there are any syntax errors or not. So I'll do the compilation. Once the compilation is done, so it will give the successful message. So afterwards, we are supposed to add a test bench. So I've already added the test bench here. So you can see the test bench is already been added. So this is the test bench. Now here the value which I need to float for executing the application, I've given some random values here. Initially I've taken both the values of A and B as 0, even the carry is 0. So this will generate 0 output. Next we have 8 as 8 has been declared for A and 5 has been defined for B. So 8 plus 5 is 13 and there is no carry. So 13 has to be displayed as 1 followed by 3 in binary representation. Similarly, 5 plus 9, 14. So 14 will be declared as 10 is A, 11 is B, 12 is C, 13 is D, 14 is E. So E will be declared as 14, but we are supposed to define the output in terms of 1, 4. And I have declared even the carry here. So it is 5 plus 9, which is 14, plus 1, 15. So since there is a carry already generated, so this will generate the output as 15, so which is 1 followed by 5. Similarly, the fourth input, 2 plus 7 is 9, and I've given a carry which is 10. So it will define the output as 1, 0. So in the last case, it is 3 and 8, so which is 11 plus 0. So the output is 11, so it should define the value as 1 and 1. Right? So I'll show you the output, how exactly the outputs are generated for this. So I'm running the test bench now. So when you see the output here, one second. So this is the output that I have received for all those 5 inputs. So in the first case, you can see here, both the inputs of A and B are 0, 0 here, and carry is also 0. So by default, sum is also 0 in this case. So in the first part, sum is 0. So in the second input position, the A value is 8, B value is 5. So 8 plus 5 is 13 and carry is 0. So the resultant should be 13. 13 will be defined as 1 followed by 3. So 1 will be declared in carry. So you can see here there is 1 here, and in sum you will have 3. So the representation will become carry followed by sum, which is 1 followed by 3, which is 13. Similarly, in the third case, I have declared the input as 5. So for A, I have declared it as 5, and for B, it is 9. So 5 plus 9, it is 14, plus 1, 15. So I should get 1, 5. So in carry, I've got 1, and in sum, I've got 5. So it is 1, 5, which is 15. In the next case, it is 2 for A and 7 for B. So it is 9 plus 1 carry, which is 10. So it should display 1 followed by 0. So I have a carry 1 and sum is 0. So which is 10. And in the last case, I have 3 for A and 8 for B. So it is 11 plus 0, which is carry. So I should get 1 and 1. So in the carry, I have got 1, and in the sum, I have got 1. So this is how we convert the hexadecimal numbers into decimal numbers or the representations uh, by making use of Verilog programming of decimal adder. Thank you all.